If you are watching this video, I'm going to surely assume that you've at least read the fundamental theorem of calculus. So basically the fundamental theorem of calculus says if you want to evaluate a definite integral that goes from x equal a to x equal b of f of x dx, then you just get an antiderivative of this function, we'll call it capital F, and you evaluate that antiderivative at b, and then you subtract from that same function evaluated at a. So the antiderivative is evaluated at the upper limit and then minus the antiderivative evaluated at the lower limit. Now, since we're subtracting, the constant would always cancel out. So when you're evaluating definite integrals, you don't have to enter the constant at the end of each of your functions. Okay, so I'm going to start you with a simple one here. Let's say we want to integrate the function 2x dx from 1 to 3. Well, first of all, we're going to find out what this integral equals. Well, if you evaluate this, you get x squared over 2 times 2. So then the 2's cancel, so you just get x squared. And this little bracket out here shows me where I'm going to integrate from. I'm going to integrate from 1 to 3. So I evaluate this antiderivative at 3, and that would give me 3 squared. And then I subtract this antiderivative evaluated at 1, which would be 1 squared. So 3 squared minus 1 squared is 8. And that's your solution. So the solution to definite integrals will always be a real number, while solutions to indefinite integrals will actually be a function. Okay, so here's another one. We're going to integrate from 0 to pi over 2 sine x dx. Now, we learned earlier that if you integrate sine x, you actually get minus cosine x. And we're going to integrate this from 0 to pi over 2. So if we evaluate this at pi over 2, we actually get 0, because the cosine of pi over 2 is 0. And then we subtract this evaluated at the lower limit, so we subtract minus cosine of 0. Well, that's minus 1. So we end up with 0 minus negative 1, which is just 0 plus 1, which is 1. Okay, now these others, I'll just go through them, and I'm going to assume you know how to integrate these functions by now. If you've watched all my other videos, you should know how to perform the integrals. So here we have the square root of x, which I need to write as x to the 1/2. And then if I apply the power rule, I get x to the 3/2 divided by 3/2. And let's see, oh, there should have been a 1/2 in front of this, so I'm sorry, I didn't put the 1/2. Okay, so this function should have been the integral of 1/2 square root of x dx from 1 to 4. And I wanted to show you that the rules for definite integrals follow the same rules we had for indefinite integrals. So you can actually factor the 1/2 out of the integral, and then you're going to evaluate from the integral x to the 1/2 from 1 to 4. And so again, like I said a while ago, that would be x to the 3/2 over 3/2. Well, then if you multiply that, that means you multiply by 2/3, so you'd have 1/2 times 2/3, which is actually 1/3. So really you would just get 1/3 times x to the 3/2. And then, or x to the 3/2 over 3. And then if you evaluate this at the upper limit, you get that would be the square root of 4, which is 2, and then 2 cubed is 8. So you would get, this would be 8/3. And then if you evaluate it at the lower limit, you would get 1 to the 3/2, and we know that would just be 1, so you would get 1/3 here. And then 8/3 minus 1/3 is 7/3 for your final answer. And then on this one, we're integrating secant squared x. And you know that when you integrate secant squared x, you're going to get tangent x. And the limits of integration are minus pi over 4 to pi over 4. So what we'll do is we'll evaluate the tangent at pi over 4, and then subtract what we would get when we evaluated at negative pi over 4. Well, the tangent of pi over 4 is 1, and the tangent of minus pi over 4 is negative 1, so we would get 1 here and then minus negative 1, and that's just going to be 1 plus 1, which is 2. Now when you evaluate definite integrals with a u substitution, you really have two approaches in the final answer. You could actually change the final answer back to u, back to the x variable, like we did when we had indefinite integrals. But in my examples, I'm going to show you how to change the limits of the integral based on the u substitution that you chose. So let's go ahead and look at this one. On this one, we're going to let u be x cubed plus 2, and then du would be 3x squared dx. Now we did this one earlier as an indefinite integral, so you should know that what I'm going to do is multiply the inside by this 3 here, and then the outside by 1/3. Then that way I have u to the 4th du here with a 1/3 on the outside. So I have 1/3 times the integral u to the 4th du. Now you'll notice here that these limits, the lower limit is 2 and the upper limit is 3. And let me just explain to you how I got that. The original limits, the lower limit was 0. So, but that was if I was going to use the variable x. But I'm going to use the variable u. So I'm going to plug 0 in up here. And you see that u is equal to x cubed plus 2. So all I want to do is find out what would the u value be if x is 0. So just plug 0 in here, and 0 cubed plus 2 is 2. So the u value would be 2 if x is 0. Then next, what would the u value be if x is 1? Well, that would be u equals 1 cubed plus 2, and 1 plus 2 would be 3. So that's how I get the lower and upper limits here, by just plugging in these x values in here and solving for the corresponding u values. Now I don't have to, when I integrate this, as long as I keep these new limits, then I don't have to switch back to the old limits. So let's see. If I integrate u to the 4th, I get u to the 5th over 5 times a third, so that's like u to the 5th over 15. And if I leave it in terms of u, I don't have to switch back to the old limits, I'll just use these new limits. So if I evaluate this at 3, then I get 3 to the 5th over 15. And if I evaluate it at 2, I get 2 to the 5th over 15. And then I just grabbed a calculator and I found out that 3 to the 5th over 15 minus 2 to the 5th over 15 is 211 over 15, or approximately 14.06. Okay, on this one I have cosine x quantity squared, so I'm going to let u be cosine x and du be minus sine x. Now since I don't have minus sine x, I'm going to multiply the inside by negative 1 and the outside by negative 1, and then that way that'll get me the negative sine x in here. So now this is going to be u squared. The cosine x quantity squared is the u squared, and the minus sine x dx is du. Now, to get the new limits, I had to let x be 0 and see what u would be. So plug 0 in for x, and cosine of 0 is 1. So the lower limit here would be 1. And then I had to plug pi in to get the upper limit. So cosine of pi is negative 1, so the upper limit for u is negative 1. And now I can just integrate this using the power rule, so I get u cubed over 3, and then I have a minus in front of it, so it's actually minus u cubed over 3. So now if I evaluate this at the upper limit, negative 1, I get minus negative 1 cubed divided by 3, and then I'm going to subtract minus positive 1 cubed evaluated at 3. Now all these signs can be tricky, so let's see, that's going to be negative 1 times negative 1, so that's going to be a third, and then I'm going to have minus negative a third, so that's going to be minus a negative a third is plus a third, so I'm going to have a third plus a third, which is 2/3. Okay, so this one here is actually very similar to the one above. And so on this one, just like the one above it, I'm going to let u equal the polynomial that's cubed. So u would be x squared minus 1, and then du would be 2x dx. So again, to get this in the proper form, I have to multiply the inside by 2. So I multiply the inside by 2, and then the outside by a half, and then that'll give me u cubed du here. And then I have to change the limits, so I plug 1 in up here for u, and then for x, and then 1 squared minus 1 gives me 0, and then when I plug 2 in up here for x, 2 squared minus 1 is 3, so the u limits would be from 0 to 3. So then I evaluate u cubed du by integrating, and I get u to the 4th over 4, and then I have times the half out here, and so I get u to the 4th over 8. And then if you evaluate that at 3, you get 3 to the 4th over 8, and then evaluate at 0, you get 0 to the 4th over 8. So I just get 3 to the 4th over 8 minus 0, which is actually 81 divided by 8. Now, let me just tell you, if you had actually replaced u with x squared minus 1 here, you could have done that, and then you would have left this limit as 1 and the upper limit as 2, and you would get the same answer, 81 over 8. Okay, let me do one where I'm posing this as an area problem. So this one says find the area bounded by this function, the x-axis, and the line x equal 3. So if you look at this function, if graphically it looks like this, and then the x-axis is below it, and the line x equal 3 is here. So all you have to do to get this area is integrate this from 0 to 3. So just integrate the function from 0 to 3, but then when I do the integration, I see that I have x squared plus 1, but it's not raised to any power on the bottom. So I'm going to let u equal x squared plus 1, then du would be 2x dx, and so then I could multiply the numerator by 2, and then multiply the outside by 1/2, and now this is du, this part is du, 2x dx is du, and the x squared plus 1 is u. And then if I plug 0 in up here for x, I get u equal 1, and if I plug 3 in for x, I get u equal 10. So the integral now would integrate from 1 to 10. And then when you integrate that, you get 1/2 times the natural log of the absolute value of u from 1 to 10. And then you just evaluate this at 10, and evaluate it at 1, and take the difference. So you can factor the 1/2 out, and then just say, okay, that's going to be the natural log of 10 minus the natural log of 1. And we know the natural log of 1 is 0, so your answer is just 1/2 times the natural log of 10 for the area. Okay, on this one, I'm going to let u equal x squared, let's say x plus 1, so I'll let u equal x plus 1, which is what I have here, and then du will be dx. And so if you go back over here and solve this for u, solve this expression for x, you get x equal u minus 1. And so we can actually change the limits of integration now from 0 to 1 to 1 to 2 since we're using u. But notice here I can actually replace x with u minus 1 here and also here, and then I get 2u minus 2 over u squared du. And then if I break that up, that simplifies to the integral 1 over u minus u to the negative 2. And we know how to integrate both of these. If you integrate 1 over u, you get the natural log of the absolute value of u. And if you integrate u to the negative 2, that's going to be u to the negative 1 divided by negative 1, which actually is just going to be plus 1 over u. And now we just evaluate this from 1 to 2. So plug 2 into this and see what you get. Then plug 1 into this and see what you get. And then just take the difference of the 2. And I left the 2 out here multiplied by both terms. And then you have 2 times what you got when you plugged 2 in, and then minus what you got when you plugged 1 in, and then multiply the final answer by 2, and you get 2 times the natural log of 2 minus 1 for the final answer. So this one required a little different type of u substitution, but we were able to get it into a form that we could integrate doing that. Now on the next section I'm going to talk about some other types of integrals.